Welcome to Class 4 of ME236 Thermodynamics 1. Should say 1 right there. We're going to take a look at the superheated phase and work through the steam tables. And so here we go. This is section 2.6, liquid and solid states. Am I correct that we're going to look through? I think so. Anyway, so here we're asking some questions, right? So here, following things in the book. Let's take a look. And where do we go here? Oh, there's me. That's what I look like. There's my office. There's my painting right there. Are you familiar with that painting? I made a copy of that painting. I painted that from Goodfellas. So let's change cameras. Can we change cameras? I think I've unplugged this camera on accident. That's why I'm showing up. I think it was because somebody called me on my phone. Don't ever call me on my phone. Maybe I should restart this video. It's starting so well. Let's see, it's going to start up. Oh, there it is. Boom. All right. And there you go. All right, so we have our notes. And what did I want to say about this? Okay, so consider some mass in the liquid condition here. All right, and we have a saturated liquid at 100 degrees Celsius. Right, so that's going to show up right here on the vapor dome. And if we look it up in our steam tables, in section B.1.1, boom, it's a good idea to tab these, by the way. And we're talking about, 100 degrees Celsius. 100 degrees Celsius, right here on there, we have a pressure. And you would imagine, okay, the saturated pressure would be the atmospheric pressure. That makes sense. And we would have a specific volume of the fluid, 0.001044. And for the gas state, 1.67290. And then here it's just the VFG, which is that one minus that one. And it's just for convenience right in there. And then, of course, if you look over here, we had internal energy. On the other facing page, enthalpy, and then entropy. You can say. But all we want to write down here for what we were asked about onto there is find the properties. All right, so we will do what they tell me. So this is B.1.1, and at T is equal to 100 degrees Celsius, the pressure, the saturation pressure that associated with that is 101.3 kPa absolutely. Sorry. But at the fluid, all right, so it's a saturated liquid that's over here. That's the VF, and you didn't memorize it, but if you were to go back and look, it would be this value, kilograms per cubic meter. We weren't asked for it, but if we were going to go over to here, this state, that would be the VG, the specific volume of the gas, 1.6729 cubic meters per kilogram. Now suppose that the pressure were to increase, suppose the pressure were to increase to 10 megapascals, right? While the temperature is held constant, right? So you can see right here, that is state 2 according to this right here, because we have 100, and they've already told us the answer that's going to be 2 right here for the state 2 or state 1. I like to draw circles around states. By the necessary transfer of heat, of course, in order to get from there to there, some heat has to be transferred. Find the properties in B.1.4. Would it be okay to assume the specific volume is constant? That's a good question. All right. So let's take a look, and I will flip and go to B.1.4. Kaboom. B.1.4. Which always seems weird thing to say. And now we're going to go to 10 megapascals, which is 10,000 kPa. And we're going to come down and take a look. And we have to go back up to the top real quick to go. Ooh, right there. Here's our V, specific volume. And boom. So write that down. 0.001039. All right. So let's just document this. At P is equal to 10,000 kPa, and temperature is equal to 100 degrees Celsius. V, right? It's not V fluid, it is fluid, but we get 0.001041 kilograms per cubic meter. Nope, I just messed up this thing up here above. Sorry. This would be meters cubed per kilogram. Meters cubed per kilogram is the correct units because it's volume per mass. Shilly. So what do we think? What do you think about this? Would it be okay to assume? We'll take a look. That's not that much difference. In fact, if you were to compare it, you would see that there's a 0.287% change. Just because you increased from like about 100 to 10,000. So that's like pretty substantial right there, right? Like 100 times, right? Did I do that right? Yeah, 100 times 100. Yeah, it should be. It should be 10,000. Yeah. So, but we only had this amount of change. So what do we assume? Yes, it's incompressible. We call that incompressible. And we will, I mean, it is a little compressible, an itty bitty amount compressible. Obviously, this is a smaller number than that. But there's really not that much change. When we go to the fluid mechanics, we'll see that liquids, water specifically, is often considered incompressible. Now, they also want to make a point here that find and compare the specific volume of saturated liquid at 10 megapascals from this table, right? So B.1.2. If we just look it up and just check out, right? So we're going to go back. Because this one, we're going to B.1.2 just because this one is indexed down there. And we will find somewhere in there, like 10, we can take a look and go over to the fluid, and we go 0.001452, right? So let's say at P is equal to 10,000 kilopascals. The temperature, the saturation temperature, I didn't write that down. The saturation temperature at 10,000 was 311.06. Not that it matters. Let's get that thing straightened out. But the VF that we find for this is 0.001452 cubic meters per kilogram. Now that's a little bit more substantial, right? Because we could look at that digit right there compared to that right there and that right there, right? So we have a pretty substantial difference. Did I write down what the difference was? So it's not really a good comparison to be approaching it this way at that, because we've raised the temperature up, so there's a certain amount of expansion that has taken place by having a higher temperature right in the thing. But if it's just pressure and pressure alone, this is the incompressibility. So it's an interesting thing to go. And this is not only is this considered a compressed liquid, it's also sometimes referred to as subcooled, right? Because they've compressed it, but they've also cooled it down some, so it's way below what its saturation temperature is going to be. It's taken away some of the saturation condition that would take place right in there. And I guess we could go ahead and go 1, 4, 5, 2, and we'll compare it to this state right here, because that's the one to compare it to. So so I went 1, 0, 4, 1 minus, and then 1, 0, 4, 1 divided. Yeah, so you have like a 39%. There's a 39.5% difference between this one and this one. But we were using this as the main one because we're saying this is correct right here for what we were thinking about, and then this is just one for comparison. So this one is 39.5% greater this one than that one. I've been 11 minutes into this. I guess maybe we got a couple things left. Let's go back to the slides. And okay, so here's the superheated steam tables. And there's a couple things to note, a couple things of importance. First off, that it's arranged. Okay, first off, it doesn't have those F's and those G's as subscripts to any of these because these are complete, right? We're not dealing with a mixed thing. It's completely vapor. So they would all be G's, if you will, if you're thinking about it that way. And then also you have a bunch of different temperatures here on each of these, and these are like little subtables. And at the heading is what the pressure is at each subtable. Now, one of the problems that we're faced is a lot of times we aren't going to be able to get the value that we want. So here is one of the most important things that we will be looking. We're going to look at interpolation and even double interpolation, and you want to be able to practice this until you get it right. So here is what a general interpolation that I've written down, and it's kind of the concept, right? So like, what if you want to get something that's like in between some numbers? Like maybe we were told get something in between 300 and 400 and something that's in between 200 and 250, right? And let's say that it was going to be this value right here, right? So that would be like we'd have to do double interpolation, but for the time being, let's just do single interpolation because it's relatively easy. So let's say that at 300 degrees, we wanted to get something in between this guy and this guy. We wanted to find out here. And it's not 225. If it was just 225, we would just take the average of it. But and that is sort of a type of interpolation. But this is called linear interpolation. What we're going to do is we're going to find the range in between here. Like let's say that was 215 and 250. We would try to find the percentage difference. But here is my routine right here. What we want to do is we're going to have 5 pieces of information. We're going to have the thing in between, let's say 215, that we're going to put into there. And we're going to try to find where the number is in between these that corresponds with 215 degrees. So that's the idea. So here is what I decided I'm going to go. I'm going to call this one A, this one B, this one C, and this one D. So I'm going to set up an interpolation, what I call an interpolation table. We'll put A here, B here, C here, and D there. Right? These are right from the table, and we'll collect them through. Now here's the known, and here's the unknown. Now you could do this in a couple different ways, but as long as you're consistent this side and this side, you'll always be able to get the right number. All right. So what I decided to write down was I'm going to go compare this and then divide by comparing that. So I'm going to say A minus K divided by A minus C. All right? And these are all values that we know, right? These are from the tables, and this is the one that's like the 215 right in there. It's going to be equal to, now we do the same pattern, B minus U, that's the unknown we want to solve for, and then B compared to D, B minus D, right? And they always have to be minuses, but they always have to be the correct pattern, right? A minus K divided by A minus C is going to be equal to B minus U divided by B minus D. Now, what essentially you're doing here is you're getting sort of the percentage of what this is, what K is, away from A and C, right? And then here's the range, and you're multiplying that range, and you're basically adding it or subtracting it with B. Now, you got to be careful with the signs. Always, treat the signs. This one, generally, the signs will cancel out to each other. So this will be a positive value. This could be a negative value because they don't always work where if this is larger than this one, this isn't necessarily larger than that one. So just be aware of that. But this guy right here, I'm going to use this a lot. But now you don't really have to memorize this, really. It's just a set of logic, and it'll work for you. So you'll see that repeatedly in the videos that follow. And the more you practice it, it can be a little bit annoying, but you can start practicing, you can get really good at it and fast at it. And that being fast at it will definitely help you complete homework assignments instead of saying, it took me 4 hours to do this. Well, I mean, honestly, if you're not practicing this thing and getting faster at it, it might take you a long time. Practice at it, get it down good, get it down well, I don't know, one of those. And you'll be able to just sling right through there. And you'll be able to finish tests early. So let's, next videos that come up are going to be practicing this. See you soon.